A rainbow isn't just colors, it's a quantum signature, written right across the sky. We think of quantum mechanics as hidden, a bizarre world of particles and probabilities. Something locked away from our senses, but its effects are everywhere, on display all around you, woven into the fabric of everyday life. This gives you a new lens. A way to see reality, to see quantum mechanics operating visibly, in nature and in technology. You see it in butterflies, how their wings wear light. Light engineered at the atomic scale. You see it in the ground beneath your feet, and why it doesn't just collapse. So look around at an ordinary object near you. It might hold a secret, a hidden quantum secret. That object near you is solid, stable, dependable, but the ground can sometimes feel like a stage for magic. There's a train that doesn't touch its tracks, it floats, a silent glider hovering, frictionless. This isn't science fiction, it's a working reality in several countries. The technology is called Maglev, magnetic levitation, and at the heart of its most astonishing version is a purely quantum phenomenon, made visible on a massive scale. Superconductivity. When you cool certain materials to incredibly low temperatures, something extraordinary happens. All electrical resistance vanishes. A current, once started, can flow forever without losing energy. It becomes a perpetual motion of electricity. But the real magic, the visible spectacle, is how this quantum state interacts with magnets. Cool a special ceramic disc in liquid nitrogen. Place it over a magnet. It doesn't just hover, it locks, it floats at a fixed height, tilted at an angle and stays there. You can rotate it. It holds its position. That's called quantum locking, flux pinning. It's a direct, macroscopic demonstration of a quantum rule. Inside the superconductor, the magnetic field gets trapped. Trapped in tiny, non-moving tubes. The material refuses to let this patterned field change, so it locks itself in place relative to the magnet, defying gravity in a way that feels like a tangible miracle. The secret behind this entire show is a quantum handshake. At those frigid temperatures, electrons normally repel each other, but they overcome that rivalry. They form delicate partnerships, Cooper pairs. Billions upon billions of these pairs move in perfect, coordinated unison, like a single, vast quantum wave. This collective dance is what expels magnetic fields. It enables that flawless, resistance-free flow. Here, the weird rules of the tiny quantum world don't stay tiny. They scale up. They engineer a new state of matter we can see with our own eyes, touch with our own hands, ride in a train. That floating train isn't just an engineering marvel. It's a rolling billboard for quantum mechanics, proving its effects can be big enough to lift us off the ground. That floating train is billions of electrons moving together. That's a quantum effect, but a single object, something you could hold made of hundreds of atoms. Does it follow the rules of solid matter, or does it follow quantum rules? To find out, they aimed something strange at a wall with two holes. Not light, not single electrons, buckyballs. These little cages of 60 carbon atoms shaped like soccer balls. They fired these molecules one at a time at a barrier. The barrier had two slits. Behind it, a detector waited to see where each molecule landed. You'd think each solid little ball goes through one slit or the other. The pattern should be two bright bands behind the slits, but that's not what happened. Over time, with thousands of buckyballs, a pattern built up on the screen. Not two bands, a series of stripes, light and dark bands like ripples from two stones in water. An interference pattern, the signature of a wave. Each individual molecule, this cluster of atoms, wasn't acting like a bullet. It was acting as if it went through both slits at once, as a wave of probability, and it interfered with itself. That's the double-slit experiment, but scaled up. To a size that feels almost tangible. The buckyball is in a superposition, a ghostly state of being in multiple places, until it's detected, and then it's forced to choose. This blurring of reality isn't just for the microscopic. It's a property of all matter. The experiment was a quiet revolution. It proved that wave-particle duality, that core quantum paradox, doesn't fade as things get bigger. It stretches into our world, visible in the data on a lab screen. The line between the quantum realm and our classical, everyday experience isn't a sharp border. It's a foggy frontier, and we are standing right in the middle of it. That line where one world meets another, it's painted in these incredible colors. There's a morpho butterfly sitting on a leaf in the rainforest, and it flashes this blue. An electric blue, a blue that shouldn't be possible. But it's not a trick of the light. It's a trick of engineering, quantum engineering. That color doesn't come from a pigment. It's not a chemical dye. If you ground the wing up, the blue would just disappear. The color comes from architecture. It's a structure, a nanoscale cathedral built by nature. The wing is covered in tiny scales, and each scale is a labyrinth. Ridges and shelves arranged with perfect, repeating precision. Physicists call it a photonic crystal. It's like a hall of mirrors for light, but so small it interacts with individual photons. When white sunlight hits this structure, most wavelengths, the reds, the yellows, they pass through the maze and they are lost. But one specific shade of blue, it finds itself in perfect sync. The peaks and troughs of its light waves, they get reinforced by the spacing of those shelves. They bounce and amplify each other. Constructive interference. It's the same principle that makes the sheen on a soap bubble or oil on water, but here it's executed with atomic-level perfection. The result is a color of pure light. Intense light, and it shifts as you move, because the angle changes the path the light takes through that tiny maze. This is quantum electrodynamics in action. The dance of light and matter, choreographed by the rules of the very small. An effect you can hold in your hand. Nature's been a master quantum engineer for millions of years. Not for calculation, but for communication, for camouflage. That flash of blue is a signal, a billboard written in the language of photons and probability. It's proof, quiet and living, that the quantum world isn't separate. It's woven right into the wing of a butterfly, painting the air with visible evidence of its rules. That butterfly wing is made of light, built by quantum rules, and those rules don't just give color. They give something more basic. They give form. Take the chair you're sitting on. It holds you up. It has a shape, a boundary. It doesn't melt into the floor. That solidity, that reliable presence, feels so ordinary it's invisible. But it's a daily miracle, a direct, visible consequence of one strange quantum law, the Pauli exclusion principle. It's a rule about personal space for particles. It says no two identical fermions, like electrons, can ever be in the exact same quantum condition. They can't share the same energy, the same spin, the same everything. It's a cosmic prohibition against overcrowding, like a theater where every seat is reserved, and no one can sit in another's lap. Now, look at an atom. The nucleus is a dense, positive core, pulling the negative electrons inward with tremendous force. Without Pauli's rule, all the electrons would crash into the lowest energy state, right on top of the nucleus. Every atom would collapse into a tiny point, but they can't, because of that rule. The electrons are forced to stack up, filling higher and higher energy levels, like filling seats from the front row to the back. This creates a pressure, a stubborn resistance to being squeezed. Physicists call it electron degeneracy pressure. It's not a force, not a push or a pull. It's a statistical standoff, a refusal written into reality to violate a quantum command. This pressure gives an atom its size, its volume. It's why atoms don't just merge into each other. When you sit in that chair, the electrons in your atoms are repelling the electrons in the chair's atoms, not through magnetic charge, but through this fundamental quantum refusal to occupy the same state. The solidity you feel is the collective defiance of countless trillions of electrons, all obeying one invisible law. Without this principle, the universe would have no structure. No stars, no planets, no butterflies, no chairs. Just a formless, collapsing soup. So the next time you lean against a wall or pick up a cup, remember. You're not just touching an object. You're feeling the palpable, macroscopic echo of a quantum rule. The Pauli exclusion principle is the silent architect of the tangible world. Holding everything together, one defiant electron at a time. That principle of defiance builds the world, but there's another quantum rule. It illuminates things with a very particular kind of light. A laser beam, it's a line drawn in pure energy. You see it in the grocery store scanner, in delicate medical surgery, in the spectacle of a planetarium show. That tight, unwavering beam, that intense dot of color, it's not just focused light, it's organized light. It's a visible army of photons marching in perfect lockstep. And its existence is a direct gift from the quantum world, a macroscopic gift. At the heart of every laser is a quantum process, stimulated emission. Albert Einstein described it over a century ago. Picture an atom. Its electrons are in an excited, high-energy state, like a ball perched at the top of a hill waiting to fall. Normally, it decays on its own. It releases a photon of light in some random direction. That's spontaneous emission. It's how most light sources work. An old light bulb. It's a chaotic, jumbled crowd of photons, but Einstein saw another possibility. What if a photon of just the right energy passes by that excited atom? That passing photon can act as a trigger. It stimulates the atom releases its energy immediately. It produces a second photon, and here's the quantum magic. This new photon is not random, it's an exact copy, same energy, same wavelength, same direction, even the same phase as the photon that triggered it. It's a perfect clone. Now imagine a material, a special crystal or gas. Many atoms are artificially pumped into that excited state. It's called a population inversion. An unnatural, energy-rich condition. When a few spontaneous photons are released, they trigger a cascade. One photon becomes two identical photons. Those two become four. Then 8, then billions, all marching in the same direction, all perfectly in sync. This is coherence. The light waves are all aligned, their peaks and troughs perfectly matched. It's the difference between the chaotic roar of a crowd and the unified chant of a stadium. The laser cavity has mirrored ends. It captures this growing wave. One mirror is fully reflective. The other lets a fraction of the light escape. The photons bounce back and forth. They stimulate more emissions with each pass, amplifying the light into an intense, coherent beam that finally shoots out through that partial mirror. What you see is a macroscopic phenomenon, born from countless microscopic, identical quantum events. So the next time you see that crisp red dot from a laser pointer, tracing a presentation slide, look closer. You're not just seeing light. You're seeing order imposed on chaos. You're witnessing a visible chain reaction of quantum clones, a direct demonstration, the strange rules of the atom harnessed to write lines of pure, coherent energy across our world. It's quantum mechanics, amplified and made brilliantly, undeniably visible. A laser beam is order made from light, but there's a substance that takes order somewhere even stranger. A liquid that refuses to obey. It climbs the walls of its container. It flows without friction, without any thickness. This isn't a special effect. It's a state of matter called a superfluid. And you can watch it happen. Helium-4, the common form of helium, when it's chilled to just a few degrees above absolute zero, something profound happens. It undergoes a phase transition more radical than freezing. It becomes a superfluid. In that state, a large fraction of the atoms stop behaving as independent particles. They lose their individual identities, they merge, they condense into a single giant quantum entity, a Bose-Einstein condensate. This is a macroscopic quantum wave. A collective dance of millions of atoms moving in perfect unison. The consequences are bizarre and visible. Pour this superfluid into a beaker. It forms a film, just a few atoms thick, that creeps up the inner walls. It climbs right over the rim, and it keeps flowing, down the outside of the beaker, until it empties itself out. It seems to defy gravity, but it's obeying a deeper rule. The rule of zero viscosity. There's no internal friction, no stickiness. Once set in motion, a superfluid can flow forever in a closed loop, a persistent current. Stir it with a tiny paddle, and you create not messy whirlpools but perfect, tiny tornadoes. Quantized vortices, their rotation isn't smooth. It jumps in distinct, precise steps. Because in the quantum world, even rotation comes in fixed packets. This isn't a subtle laboratory curiosity. It's a dramatic, observable rebellion against everything we know about classical fluids. It's a lake that could, in theory, flow uphill. A river with no banks. Here, the quantum statistics that govern identical particles called bosons don't just influence behavior. They take complete command. They dictate how an entire cup of liquid will move. So when you see a video of liquid helium performing its impossible climb, you're not watching a trick. You're watching a cupful of atoms surrender their individuality. You're seeing a quantum collective. A tangible, sloshing, climbing proof that the rules of the very small can orchestrate the behavior of the very visible. Giving us a fluid that remembers only the laws of the quantum world. The Aurora is a quantum event happening across the entire sky. It starts with the sun. The sun sends out a stream of charged particles, the solar wind. That wind travels to Earth. It meets our planet's magnetic field. Most particles get deflected away. But some get caught. They follow the magnetic field lines down toward the poles. They funnel into the upper atmosphere, 60 to 200 miles up. And there they collide. These solar particles, mostly electrons, smash into atoms, oxygen and nitrogen atoms. The collision transfers energy. It gives the atom a quantum kick. It knocks an electron inside the atom into a higher energy state. That state is unstable. The electron can't stay there. It has to fall back down, and when it falls, it releases that extra energy. It releases a photon, a particle of light. The color of that light is specific. It's determined by the atom's structure. For oxygen, one particular drop produces that pale green. The common aurora color. A different, rarer drop in oxygen, higher up, makes a deep red. Nitrogen can give blues or purples. Every shimmer you see is billions of these events. Billions of electrons making jumps. Each jump emits a pinpoint of colored light. The solar wind brings the energy. The magnetic field directs it. But the light itself comes from the atom. From those quantized energy levels, so the aurora is a connection. A chain from the sun's furnace down the magnetic field, ending in a flash inside a single atom. The night sky is glowing from quantum leaps. That aurora in the sky is light from quantum leaps. But there's another kind of quantum leap, one you're holding right now. It's the reason your photos, your files, they don't just disappear when the power goes off. That's flash memory, and the whole thing works because of a quantum trick. Tunneling. Inside a USB drive or an SSD, there are billions of tiny switches. They're transistors, but with a secret, a floating gate. It's like a little bucket. An isolated bucket, surrounded by insulation. To save data, you fill that bucket with electrons. That's a 1. To erase it, you empty the bucket. That's a 0. But there's a problem. That insulation is a wall, a classical barrier. The electrons in the circuit, they don't have the energy to get over it. They should be stuck. Your data could never be written, never erased, but quantum rules are different. In that world, particles aren't just little balls, they're waves, probability waves. And a probability wave doesn't see a solid wall. It sees a hill, and there's a chance, a real probability, that the wave can just appear on the other side. The particle doesn't go over. It goes through, it tunnels. This isn't a metaphor, it's a direct effect. The electron, because it's wave-like, has a finite probability of being inside the barrier. A classically forbidden place. And sometimes it pops out on the far side. It's like throwing a ball at a mountain, and instead of bouncing back, it just materializes on the other slope. Engineers use a precise voltage. They make that probability high enough. They coax billions of electrons to do this, to quantum tunnel across an insulating gap they shouldn't be able to cross. They fill the floating gate for a 1, reverse the voltage, and they tunnel back out for a 0. That's how your device writes, how it erases. Without this tunneling, modern flash memory wouldn't work. This storage, it would be impossible. So when you save a file, you're not just clicking. You're commanding an army of electrons to perform a microscopic quantum miracle. Trillions of tunneling events in perfect silence to save 1 moment. Your whole digital world rests on that, on particles doing the impossible, built not just on silicon, but on the permeable, probabilistic fabric of quantum reality. That digital world is built on electrons tunneling through walls. But imagine the walls themselves are made of nothing, just empty space, and they still push. That's the Casimir effect, a force that comes from pure nothingness. It's one of the clearest signs that the quantum world isn't just particles, it's about space itself. So you take 2 perfectly smooth, uncharged metal plates. You put them in a perfect vacuum, a completely empty space, and you bring them incredibly close together. Closer than 1,000th of a hair's width. And then something impossible happens. They move, they pull toward each other. This gentle, measurable attraction just appears. Classical physics can't explain it. There's no gravity, no magnetism, no charge. So what's pulling them? The answer is in redefining nothing. In our everyday view, a vacuum is empty. A void. But in quantum field theory, the vacuum is alive. It's this seething, bubbling sea of potential. A field of infinite energy. And in it, pairs of virtual particles and antiparticles are constantly flickering into existence. They borrow energy from the vacuum for a moment, then annihilate and vanish. We call them virtual because we can't detect them directly, but their effects are real. These are quantum fluctuations, and they come in all wavelengths, like waves on an energetic sea. Now you bring in those 2 plates. They act as boundaries. They set rules for what waves can exist in the space between them. Only certain wavelengths fit. Waves that are whole multiples of the gap. All other wavelengths are excluded. Outside the plates, in the open vacuum, all wavelengths are possible. The quantum sea is unrestricted. That creates a pressure difference. There are simply more possible fluctuations, more virtual particles, pushing on the outside of the plates than between them. The greater external pressure squeezes the plates together. It's not magic. It's a quantum pressure difference, a force born from restricting possibilities. The Casimir force is that ghostly push made visible. In labs with exquisitely polished plates and sensitive instruments, this attraction has been measured. It matches quantum theory perfectly. So when you think of empty space, remember, it's not empty. It's a dynamic, energetic medium. The Casimir effect is its signature. A tangible, macroscopic force that proves nothingness has a structure. A quantum structure. And sometimes that structure can reach out and move the physical world. That force from nothingness pushes plates together, but there's another quantum rule. It locks magnetic fields into place, makes them step, not slide. That's flux quantization. You can see it in a ring of superconductor, just a simple loop. When you cool that loop down into its superconducting state, something happens to any magnetic field trapped inside. The field isn't free to be any strength. It's forced into specific, discrete values. It's quantized. It's like trying to fill a glass with water, but the water only comes in exact cupfuls. You can have 1 cup, 2 cups, 3, but never 1.5. The magnetic flux through that ring does the same thing. It comes in whole number multiples of a tiny, fundamental unit. A magnetic quantum. This happens because of the collective quantum wave. The wave function of all those paired electrons moving together around the ring. For that wave to make sense, it has to be consistent. If you follow it all the way around the loop, it has to return to itself. It has to be single-valued. No weird twist, no phase mismatch. That requirement, that need for self-consistency, puts a strict condition on the magnetic field passing through the center. The field has to adjust so the electron wave's phase, shifted by its presence, comes out exactly right after 1 full trip. The math forces the enclosed magnetic flux to be an integer. A whole number, 0, 1, 2, 3 times that fundamental flux quantum, nothing in between, and this isn't a microscopic suggestion, it's a macroscopic mandate. In the lab, scientists use devices called SQUID, superconducting quantum interference devices. They're essentially loops with a tiny weak link. They can detect changes in magnetic flux so small they're a fraction of that quantum step. The current through a SQUID doesn't change smoothly as the magnetic field changes. It jumps, it oscillates. Each peak and trough corresponds to the flux in the loop ticking from one quantum number to the next. You can watch the readout, see the discrete steps. Here, the abstract idea of quantization isn't hidden in atomic spectra. It's written directly into the behavior of a magnetic field you can measure. A field big enough to hold in your hand, trapped in a ring. So quantum discreteness, it's not always about tiny particles in boxes. Sometimes it's about the magnetic signature of the universe itself. Forced to count in whole numbers, proving that even on our scale, nature sometimes moves in precise, quantum leaps. That magnetic field gets locked into whole numbers. A quantum step. But if you could tune a particle's energy just right, it could become a universal ruler. That's the Mössbauer effect, a near-perfect resonance. It comes from a quantum trick with recoil. Think of an atomic nucleus like a tiny bell. When it's excited, it rings, it emits a gamma ray, a burst of high-energy light. But there's a problem. When the nucleus fires that gamma ray, it recoils, like a cannon kicking back. That recoil steals a tiny bit of energy from the gamma ray. It shifts the frequency. Now take another, identical nucleus. To absorb that gamma ray, the energy has to be exactly right. The incoming gamma ray has to match the precise energy gap inside the waiting nucleus. But because the first gamma ray lost energy to recoil, its frequency is off. It's like trying to unlock a door with a key that's been filed down. The second nucleus can't absorb it. Resonance fails. Rudolf Mössbauer found something brilliant. You embed the radioactive source nuclei in a solid crystal. At very low temperatures, the quantum rules change. The nucleus isn't free. It's bound to a vast lattice of atoms. When it emits its gamma ray, the recoil momentum isn't taken by a single nucleus. It's distributed across the entire crystal. The crystal is so massive that its recoil is vanishingly small, practically zero. The gamma ray gets emitted with its full, pristine energy, no loss. This is recoil-free emission, a quantum effect where the entire crystal acts as one object. The gamma rays produced are incredibly sharp. Their energy is defined with phenomenal precision. Now you can use these gamma rays as a probe. Aim them at a target material, also embedded in a crystal. If the energy levels in the target nuclei match, they absorb the gamma rays perfectly. If there's even a minuscule difference, absorption drops. That's Mössbauer spectroscopy. It's so sensitive it can detect the influence of a single electron's magnetic field on the nucleus. Or the subtle changes in gravity predicted by Einstein. In one famous experiment, physicists used this to test general relativity. They put a gamma ray source at the bottom of a tower and a detector at the top. The gamma rays, climbing against gravity, should lose a tiny bit of energy, a redshift. The Mössbauer effect was precise enough to measure that infinitesimal shift. And it confirmed Einstein's prediction. Here, the quantum behavior of a nucleus locked in a crystal lattice creates a tool of macroscopic precision. It lets us measure the fabric of spacetime, or analyze the iron in ancient pottery to see how it was fired. From the heart of the atom to the scale of human discovery, this quantum trick bridges the gap. It proves the hidden world of the nucleus can write its signature across our own, in data and in confirmed theory. That Mössbauer ruler measures the fabric of space. But there's another measurement for electricity. It's so perfect it sets the global standard. You get it when you trap electrons in a flatland. You take a very pure semiconductor, cooled almost to absolute zero. You put it in an immensely strong magnetic field, pointed straight down. And you confine the electrons so they can only move in a two-dimensional plane. Like beads on a table, under those conditions something emerges, the quantum Hall effect. You measure the electrical resistance across this flat electron sea. As you increase the magnetic field, the resistance doesn't change smoothly. It forms a staircase. It jumps to a specific value, then holds perfectly steady, a plateau, as the field changes. Then it jumps to the next step, and the next. These resistance values are exact. They are defined by fundamental constants, Planck's constant and the charge of the electron. The resistance on the first plateau is exactly 25,812.8 ohms, with unimaginable precision. That's the von Klitzing constant. A number written into the quantum code of the universe. What's miraculous is it's universal. It doesn't matter if the material is gallium arsenide or graphene. It doesn't care about impurities or the sample shape. The exact same number appears, because the effect doesn't come from the material's ordinary properties. It comes from the topology of the electron wave functions in that magnetic field. Topology is the math of shapes that don't change under smooth deformation. A coffee mug and a donut are topologically the same, each with one hole. Here, the collective quantum state of all the electrons acquires a topological invariant. A global property that's either there or not. It's an integer, a whole number, and that integer directly dictates the resistance you measure. On each plateau, that integer is locked in. That's why the resistance is so perfectly flat. The electrons on the edges of the sample form one-way conductive channels, immune to disorder. The bulk of the material becomes an insulator. It's a quantum state so robust that metrologists now use it to define the ohm. Our unit of electrical resistance is no longer based on a physical artifact in a vault. It's based on a quantum phenomenon we can reproduce in a lab. A phenomenon where the geometry of an abstract quantum space dictates a tangible property. Something we can measure with wires and dials. So when an engineer calibrates a sensitive instrument, they're invoking this flat, cold world of trapped electrons and intense magnetic fields. They're using a quantum staircase, visible on an oscilloscope, to anchor our entire system of electrical measurement. The quantum Hall effect shows the deepest rules of reality don't just whisper in atoms. They can shout in resistance, and we've learned to listen. The quantum staircase sets our electrical standards, but you could take that idea of a collective state and make it visible. As a cloud of atoms so cold they lose their individuality completely. That's the Bose-Einstein condensate, in its purest form made in a lab. In the 90s, scientists did something profound. They used lasers and magnetic traps to cool a cloud of rubidium atoms to a temperature just a whisper above absolute zero. At that extreme cold, something happens. The atoms slow way down. Their quantum wave nature, usually hidden, starts to swell. Their matter waves, the probability clouds, they begin to overlap. They merge, and at a precise critical temperature, they go through a phase transition. They condense, not into a liquid or a solid, but into one single, giant quantum state. A superatom, millions of particles start to march in lockstep. They're described by one wave function, one collective identity. You can see it under a microscope. Before condensation, the cloud is diffuse, a fuzzy halo. After a dense, sharp peak appears right in the center. That peak is the condensate, a blob of quantum matter, hundreds of micrometers across. Macroscopic for the atomic world, and it behaves in quantum ways, spectacularly. Release it from its trap and it expands. But because it's one coherent wave, it interferes with itself. Create two separate condensates and let them overlap. They form a clear interference pattern, stripes, high and low atom density, just like light waves. This is matter interfering with itself on a scale you can photograph. You can stir it, and it forms quantized vortices like a superfluid. You can even extract atoms from it in a coherent beam. Creating an atom laser. A beam of matter, not light, where all the atoms are in the same quantum state. The creation of these condensates was a landmark. It gave us a new kind of matter, a quantum matter where the statistics that govern Boson's particles that love to be together take full command. Here in the lab, we don't just infer quantum behavior from indirect signals. We can poke it, prod it, split it, watch it coalesce. We have a tangible, visible playground where the rules of the quantum world are the only rules that apply. It's a direct window, a place where the bizarre becomes ordinary, and the invisible becomes a cloud you can see. That cloud of atoms is a quantum object we can see. But there's another one we see every day. The sun, that light, the white warmth, it's not simple. It has a precise signature, and a century ago, that signature broke classical physics. It started the quantum world. It's called the Blackbody spectrum. Imagine a perfect emitter, an object that absorbs all light and re-emits it based only on its temperature. In theory, cold, it would be perfectly black. That's the name. A star, like our sun, is a near-perfect example. The light it gives off across all colors, it forms a specific curve. Predictable, the intensity at each wavelength depends only on temperature. Classical physics tried to describe this, using electromagnetism and thermodynamics. The prediction was a disaster. It said any hot object should emit infinite ultraviolet light, and beyond, an absurdity, the ultraviolet catastrophe. By that logic, the sun should instantly blast the universe with lethal radiation. But the world wasn't like that. The red glow of a cooling ember, the yellow-white sun, the blue of a hotter star, they followed a different curve, smoother. Max Planck made a desperate move to fix the math. He proposed something radical. He said the atoms in a hot cavity's walls couldn't vibrate with any energy. Only energies that were whole number multiples of a tiny, fundamental unit. Energy wasn't a smooth flow, it came in packets, quanta. He didn't believe it was physically real. To him, it was a mathematical trick. But when he put this quantum idea into the equations, the ultraviolet catastrophe vanished. The new curve matched the observed spectrum. Stars, hot objects, it fit perfectly. The Planck law was born. This means something profound. The white light from your window, it isn't just sunlight. It's the integrated glow. Trillions upon trillions of discrete quantum jumps. Inside the sun's furnace, atoms are constantly excited and then fall back down, emitting photons. The sheer temperature averages those individual events into that smooth, familiar curve. A star's color directly tells you its temperature because of this quantum rule. A cooler star is redder. A hotter star is bluer. Every point on that curve is proof of the graininess of energy. So when you look up at the night sky, you're not just seeing distant suns. You're reading a cosmic chart, a chart written in the language of quanta. The twinkle of each star is a macroscopic fingerprint, a direct, visible output of the quantum mechanics in its fiery heart. That light traveled across space and time to reach your eyes, and it carries the proof that our universe is fundamentally quantized. That light from a star is a quantum printout. But there's a device that can read the faintest magnetic whispers of your own body. It listens to the hum of your thoughts. That's the Josephson effect. Where quantum phase becomes a superpower for measurement, you take two superconductors, they're not touching. You separate them with an insulating barrier. So thin it's barely there, a nanometer or two. In the classical world, that's a perfect block. No current can cross an insulator. But in the quantum world with superconductors, something else happens. A direct current can flow across that gap. With zero voltage applied, it just flows. That's the DC Josephson effect. It seems to defy logic. How can electricity cross an insulating wall without any push? The answer is in superconductivity itself. Those Cooper pairs, the coupled electrons moving as one quantum wave. That wave has a phase, a rhythm. In a single superconductor, the phase is uniform. But with two superconductors close together, separated by that thin barrier, their quantum waves can talk. The Cooper pairs don't smash through the barrier. They quantum tunnel through it. Because they are waves and the phases of the two waves become coupled. They lock in step across the gap. This phase coherence is what allows a supercurrent to flow perpetually, without any driving force. It's quantum mechanics on a macroscopic scale, a measurable current dictated by the phase difference between two quantum objects. Now, build a loop with two of these junctions. You have a superconducting quantum interference device, a SQUID, simple in concept, breathtakingly sensitive in practice. Any tiny magnetic field threading that loop will change the phase relationship around it, and that change modulates the supercurrent you can measure. The result is a magnetometer of almost unimaginable sensitivity. It can detect magnetic fields 1 billion times weaker than the Earth's, fields so faint they come from the electrical activity of your neurons firing, or the gentle pulsing of your heart muscle. In hospitals and research labs, arrays of SQUID are used for magnetoencephalography, mapping the magnetic fields of the brain. They create images of neural activity without a single electrode touching the skin. They can also do magnetocardiography, listening to the heart's magnetic signature. This isn't science fiction. It's a routine diagnostic tool born from quantum physics. So a patient in a brain scan is having their thoughts translated by a quantum device. The Josephson junction transforms an invisible quantum relationship, the phase coherence of a wave function, into a current we can measure. And that current becomes a window into subtle magnetic landscapes, from the geology of rocks to the living electricity inside us. It proves quantum phase isn't just a mathematical abstraction. It's a physical quantity, one we can wire into a circuit and use to listen to the quiet hum of life itself. A star's light is a kind of quantum printout. But the story doesn't end when the star dies. Its final form can be this ghostly ember, a white dwarf. A single teaspoon of that material would weigh tons here on Earth. And that's not science fiction. It's a direct prediction of quantum mechanics, written in the sky. When a star like our Sun runs out of nuclear fuel, it can't fight gravity's inward crush anymore. The outer layers puff away. What's left is the hot, dense core. That core, rich in carbon and oxygen, should collapse under its own weight, but it doesn't. It stabilizes, it becomes a white dwarf, glowing with residual heat for billions of years. What stops the collapse isn't fire. It's not nuclear fusion. It's a quantum rule. The same rule that gives your chair its solidity, the Pauli exclusion principle. As gravity squeezes the stellar core, it packs electrons into a smaller and smaller volume. But those electrons, like stubborn citizens, refuse to share the same quantum state. They can't be forced into the same energy level. That refusal creates an outward pressure. Electron degeneracy pressure. It's a quantum mechanical standoff against the immense force of gravity. That pressure is so powerful it can support a mass up to about 1.4 times our Sun's mass, packed into a sphere the size of Earth. Beyond that limit, the Chandrasekhar limit, even this quantum defiance fails. Gravity wins, and the star collapses further into a neutron star or a black hole. But within that limit, a white dwarf stands, a celestial monument to a quantum law. The light we see from these distant cinders through our telescopes isn't just the glow of cooling matter. It's the visible signature of a star being held up by the collective will of its electrons. They obey a command from the smallest scales, a command that says you cannot occupy my space. And that command echoes across light years, sculpting the afterlife of stars. It means when we observe the quiet, steady light of a white dwarf, we are witnessing quantum statistics in action. On a cosmic stage, proving the rules that govern particles in a lab also govern the fate of suns. That white dwarf is held up by a quantum refusal. But then you think about a single atom. The simplest one, hydrogen, a proton and an electron. Its energy levels were perfectly described by the Schrödinger equation. That was the textbook model. But in the late 1940s, Willis Lamb and Robert Rutherford looked closer. They used a new technique, microwave spectroscopy. They measured the energy difference between two specific states of hydrogen. states that, according to the basic theory, should have had exactly the same energy. They were degenerate, but Lamb found they were not. There was a tiny split. A shift, the Lamb shift. It was minuscule, a difference in energy corresponding to a frequency of about 1057 MHz, a whisper in the data. But in physics, whispers can be revolutions. This tiny discrepancy meant something was missing. The electron wasn't just orbiting a bare proton in empty space. It was living in a vacuum that was not empty. According to quantum electrodynamics, the vacuum is a seething sea of virtual particles. Pairs of electrons and positrons, photons, flickering in and out of existence. These quantum fluctuations of the electromagnetic field create a sort of froth. And the electron in its orbit is constantly interacting with this froth. It's like wading through a shallow, choppy sea. That interaction with the fleeting virtual particles slightly alters its effective mass, its coupling to the proton. It smears its position ever so slightly. And that smearing changes the energy levels. The most famous effect is that it pushes the two s orbitals to a slightly higher energy than the p orbitals. Breaking the degeneracy, that's the Lamb shift. It's a direct signature of the electron dancing with the ghostly activity of the vacuum. To confirm it, theorists like Julian Schwinger, Richard Feynman, and Shinichiro Tominaga had to develop the full mathematical machinery of quantum electrodynamics. Renormalization, a way to tame the infinities from these vacuum interactions. The Lamb shift became the critical test. The experiment demanded a theory, and the theory, once developed, predicted the shift with stunning accuracy. The numbers matched. This wasn't just a tweak. It was a validation of our deepest understanding of light and matter. So when a physicist today measures the spectral lines of hydrogen with extreme precision, they are not just reading the atom's barcode. They are detecting the faint imprint of the vacuum's quantum structure, a structure with real, tangible effects. It proves that what we call empty is a dynamic medium. And its quantum whispers nudge the very building blocks of reality, leaving a mark we can find in the light. The spectral lines of hydrogen, they carry this whisper from the vacuum. But the quantum world can whisper in another way, through a place where nothing seems to happen. That's the Aharonov-Bohm effect. It reshapes how we think about cause and influence. An electron is a tiny charged particle. In classical physics, the only thing that moves it is a force, an electric field, a magnetic field. So if an electron moves through a region where both fields are exactly zero, it should feel nothing. Its path should be straight, uneventful, but in the quantum world that breaks down. Here's the experiment. You take a beam of electrons and split it into two paths. Like a fork in the road. These two paths go around a long, thin solenoid. A solenoid is just a coil of wire. When you run a current through it, it creates a strong magnetic field inside the coil. But outside the coil, where the electrons actually travel, the magnetic field is zero. The electrons never pass through any magnetic field. They travel through a perfect magnetic void. After the paths recombine, the electrons hit a detector. They make an interference pattern, light and dark bands, because each electron behaves as a wave, and the two waves interfere. Now you turn on the current in the solenoid. The magnetic field inside it springs to life. The electrons outside still experience zero magnetic field. They feel no classical force. But when you look at the detector, the interference pattern shifts. The bands of light and dark move. Something changed the electron's wave, even though it traveled through empty space. That something is the electromagnetic potential. In quantum mechanics, the wave function of a charged particle is directly sensitive to this potential. It's like a background field, a landscape of influence that exists even where forces are absent. As the electron's wave travels around the solenoid, the two paths enclose that region of magnetic flux. The presence of that flux, even though it's never touched, gives a different phase shift to each part of the wave. It's like two runners going around opposite sides of a spinning carousel. They both run on flat ground, but the spinning object changes their relative timing when they meet. When the waves recombine, their phases are different because of that enclosed flux. That changes the interference pattern. The shift is measurable, precise, and it depends only on the amount of magnetic flux inside the solenoid. It's a topological effect. The shape of the paths doesn't matter. The details of the solenoid don't matter. Only whether the path encloses the flux or not. This result was startling. It meant that in quantum theory, the electromagnetic potentials aren't just mathematical tools. They are physically real. They have direct, observable consequences. The electron is aware of the topology of its journey. It remembers what it encircled. So the Aharonov-Bohm effect gives a new lens. Influence in the quantum realm can be non-local. Topological. An electron can be touched by a magnetic field it never enters, guided by a presence hidden in a space it never visits. The void isn't so empty. It's filled with potentials that write their signature into the dance of matter waves. A signature we see in the shifting lines of an interference pattern. A clear testament that the quantum world connects things in ways our classical intuition could never foresee. The Aharonov-Bohm effect shows an influence without a force. But then you have to ask, what if the particles themselves could change what they are? And in the fractional quantum Hall effect, they do. It's the stranger, deeper cousin of the integer effect. It shows up when you take that two-dimensional electron gas and cool it even further, much closer to absolute zero. Then you apply a magnetic field that's far stronger, much more immense than before. Under those conditions, the electrons are pushed into an even tighter dance. They interact so strongly that they lose their individual identities. They form a new quantum liquid. A collective state, so entangled it gives rise to particles that shouldn't be possible. Quasi, particles with a charge that's a fraction of the electron's fundamental charge. 1/3, 1/5, 2/7, these aren't broken pieces of an electron. You can't isolate a third of an electron. They're excitations, ripples in this dense, correlated quantum sea. Each one behaves as if it carries a fraction of the charge. It's an emergent property, a collective fiction that becomes a measurable reality, and this has a direct, macroscopic signature. The Hall resistance doesn't just step in whole numbers of that constant, it steps in precise fractions of it, a staircase with finer, fractional steps. The precision is just as absolute, just as universal. This fractional quantization is a triumph of quantum many-body physics. It shows that when you confine electrons to a flatland and put them under extreme conditions, they don't just obey simple rules. They collaborate to write new ones. They condense into a topological phase of matter, a phase where the ground state has a kind of quantum order that's globally protected. The fractional charges and the precise resistance are the fingerprints of that order. It's a stable, new world of matter, engineered by quantum mechanics itself. Discovered in the lab and measured on our instruments. So when physicists chart that fractional resistance plateau on a screen, they're not just recording data. They're mapping the shoreline of a new quantum continent, a place where the collective mind of electrons invents its own rules, and those rules become as real and as measurable as the voltage in a wire. It might be the purest example of how the quantum world, when given enough particles and the right stage, doesn't just hide, it creates. It composes entirely new symphonies of matter and lets us hear their precise, fractional notes. That fractional world is one of pure quantum invention. But sometimes the most profound quantum effects are the ones we look right through. A window pane. It's so ordinary we forget to question it. Why is glass clear? Why does it let light pass while a brick wall or a piece of wood does not? The answer isn't found in the chemistry of sand and soda. It's found in the quantum architecture of its atoms, in the forbidden zones of electron energy. Every solid has a structure of allowed energy levels for its electrons. Think of it as a multi-story parking garage. The lower floors, all filled with cars, are the valence band. The upper, empty floors are the conduction band. Between them is a gap. The band gap, a no-parking zone, For an electron to absorb a photon of light and jump from the valence band to the conduction band, the photon must carry at least enough energy to cross that gap. Now consider visible light. It's a small slice of the electromagnetic spectrum. Each color corresponds to a specific photon energy. Red photons carry less energy, violet photons carry more. In a material like silicon used in solar panels, the band gap is just right. It matches the energy of many visible and infrared photons. Those photons are absorbed, their energy used to free electrons. That's why silicon isn't transparent. It's a dark, absorbing solid. But in silica, the main component of glass, the atomic arrangement creates a much wider band gap. The energy needed for an electron to jump is greater than the energy carried by any photon of visible light. To the electrons in the glass, the entire rainbow is too weak. It's like trying to throw a ball over a skyscraper. The photons simply don't have the quantum ticket for admission. They cannot be absorbed, so they do the only thing they can. They pass through. They interact very little with the material, that's transparency. This is a quantum filter operating on a macroscopic scale. The clear view of your backyard, the distorted view through a bottle, the brilliant sparkle of a crystal chandelier, all of it is governed by this invisible energy landscape. Ultraviolet light, with its higher energy photons, can sometimes cross that gap. That's why some glasses block UV. They've been doped with materials that absorb those specific energies. And infrared heat radiation, with lower energy photons, can make atoms vibrate directly, which is why glass can feel warm even as it remains see-through. So when you look through a window, you are not just seeing the world outside. You are experiencing a quantum selection rule, a law written in electron volts and probability. The very reason we can have greenhouses, telescopes, eyeglasses, and skyscrapers curtained in light is because of this precise quantum alignment in a humble material. Our vision, framed by glass, is literally filtered through the forbidden zones of the atomic world. A clear, daily reminder that what we perceive as empty space is often just a domain where light lacks the quantum key to be stopped. Glass is transparent because of a quantum filter for light. But light can do more than just pass through. A single particle of light can knock an electron free and start a current. That's the photoelectric effect. It's the silent quantum engine inside every solar panel. You look at a rooftop array, those dark sheets soaking up the sun. They seem passive, quiet, but on the atomic scale there's a storm, a harvest of individual quantum events. Classical physics said light was a wave, a continuous stream of energy. If that were true, a dim light on a metal should eventually build up enough energy to knock an electron loose. But that's not what happens. A dim light, no matter how long it shines, does nothing if its color is wrong. A bright blue light, even for an instant, can eject electrons immediately. It was a puzzle. Albert Einstein solved it in 1905. He took Max Planck's idea of quantized energy and ran with it. He proposed that light itself is quantized. It comes in packets, particles we now call photons. Each photon carries a specific amount of energy tied to its color. Blue photons carry more energy than red photons. In the photoelectric effect, a single photon strikes a single electron in the material of the solar cell. It's a one-to-one collision. If the photon's energy is above a certain threshold, the material's work function. It can transfer all its energy to the electron. The electron is liberated, knocked free from its atomic bond. That creates a hole, a positive charge where it used to be. In a solar cell, this isn't random. The material is engineered. It's a semiconductor with a built-in electric field. This field immediately sweeps the freed electron in one direction and the hole in the other. It prevents them from recombining. That separation of charge is a voltage. Connect a wire and the electrons flow. They become an electric current. One photon, one electron. Billions of photons per second, billions of electrons. That microscopic trickle becomes a macroscopic current. Enough to charge a battery, power a home, or light a city. So the electricity from a solar panel isn't some vague conversion of sunlight. It's a direct, particle-for-particle transaction, a quantum mechanical exchange. Every watt on the meter is the sum of countless individual photons paying their energy to free countless individual electrons. The panel on your roof is a quantum counting machine, ticking with each photon strike, turning the particle nature of light into a tangible river of power you can use. It's a daily, visible proof that light is both wave and particle. And we've learned to build technology that listens to its quantum voice. That solar panel works photon by photon, but light can also carry information. It carries a kind of fingerprint from the atom, a spectral line, and that fingerprint can shift. If you put an atom inside a magnetic field, the light it gives off changes. Those sharp spectral lines, the unique colors for each element, they don't just get fuzzy, they separate. They split into distinct lines very close together. That's the Zeeman effect. It's like the atom's internal compasses are all aligning with that outside magnetic force. Electrons have this property, spin, which is a tiny intrinsic magnetism. Their orbits also create a magnetic moment. So in a magnetic field, the energy of those quantum states shifts a little, depending on how they're oriented. States that used to have the same energy now have different energies. So when an electron drops down to emit light, the photon's energy is slightly different depending on which shifted state it started from. One line becomes 2 or 3 or more. You can see it with a good spectroscope. It's a direct, visible sign that the atom's quantum states aren't isolated. They respond to the world around them. Astronomers use this all the time. They look at light from a star or a distant gas cloud, and they can detect that splitting of the spectral lines. And that tells them the strength of the magnetic fields out there in those faraway places. They're reading the magnetic signature of the cosmos, written in that split light. Now do the same thing but with an electric field. That's the Stark effect. Here, the external electric field pulls the positive nucleus and the negative electron cloud in opposite directions. It distorts the atom's shape just very slightly. And that distortion also changes the energy levels. It lifts degeneracies, and that causes the spectral lines to split and shift. This effect is strong in places like stellar atmospheres, where you can have immense electric fields in plasmas. On Earth, it's used in labs to study atomic structure with incredible precision. Both effects turn a simple color of light into a rich stream of data. That single line of red or blue becomes a multiplet, a little family of lines. The spacing between them, their intensity, their polarization, all of it is a code. A code that reveals the invisible forces acting on the atom. So when a physicist adjusts a magnet near a gas tube and watches a spectral line split in their instrument, they're seeing a quantum interaction made visible. They're seeing the atom's internal quantum landscape being gently tilted by an external hand. The light carries that story. It proves an atom isn't a sealed fortress. It's a sensitive quantum instrument, constantly reporting on the forces that surround it. And we've learned to listen to that split-voice testimony, using it to map magnetic fields across the galaxy and to probe the electric hearts of stars. That split-voice testimony from an atom is a record of influence. But then you have to ask, what if the record could be changed after the event? What if the past could be rewritten by a choice you make now? That's the quantum eraser experiment, a demonstration that seems to bend time. The idea at the heart of it is simple: information matters. In the quantum world, what you know or what you can know, it shapes reality. We saw this with Buckyballs. A molecule acts like a wave, goes through both slits, makes an interference pattern. But if you set up a detector to see which slit it actually goes through, that pattern vanishes. You get two clumps. Gaining which path information forces the molecule to behave like a particle. The wave behavior collapses. The quantum eraser asks a deeper question. What if you get that information and then you deliberately lose it? Can you undo the collapse? The setup is intricate, but the principle is this. Scientists use a source that emits pairs of entangled photons. Think of them as quantum twins born linked. What happens to one instantly influences the other. One photon, the signal photon, goes toward a double slit. Its twin, the idler photon, goes on a different path. Now, clever optics after the slits can mark which path the signal photon took. This tagging is done by giving the idler photon a distinct property depending on the signal photon's path. If you then measure the idler photon in a way that reads this tag, you know the signal photon's path. And just like before, the interference pattern for the signal photon disappears. Its wave nature is lost, but here is the eraser. You can choose to measure the idler photon in a different way, a way that doesn't reveal the path information. You scramble the tags, you erase the which path data from the universe, and when you do that, and you look only at the signal photons whose twins were measured in this scrambled way, something happens. The interference pattern comes back. The fringes reappear. The wave behavior is restored. The most mind-bending version is the delayed choice quantum eraser. In this setup, the choice of how to measure the idler photon, to learn the path or to erase it, can be made after the signal photon has already hit the detector screen. Its fate is already recorded. Yet, when the data is sorted later, based on that later choice, the pattern changes. Photons that were recorded as dots in a particle-like clump get reclassified into a wave-like interference pattern. All based on a decision made about their twin after they were gone. This feels like a paradox. It seems to suggest the present can reach back and alter the past. But most physicists see it differently. They say it shows that until a measurement completes the chain of information, quantum events are not fixed. The signal photon's behavior isn't decided until the entire, entangled system is measured in a specific way. The pattern on the screen is a macroscopic history, but it's a history that remains ambiguous, a superposition of possibilities, until the final piece of information from its entangled partner arrives to provide context. So the quantum eraser doesn't literally rewrite time. It reveals that in the quantum realm, there is no single objective sequence of events independent of observation. What we call the past is a story written by the questions we finally choose to ask. The fringes on that final screen are the answer, a testament that reality, at its most fundamental level, is a tapestry of correlations and potentialities, waiting for information to give it its final classical form. A pulsar has this steady rhythm. It pulses with a regularity that rivals atomic clocks, but it's not a mechanical tick. It's the spin of a star, a neutron star. It's city-sized and it beams radiation like a lighthouse across space. And that star itself, that impossibly dense object, it's a monument to quantum defiance. When a massive star explodes in a supernova, its core collapses under gravity. Electrons get crushed into protons, forming neutrons. The whole core becomes an ocean of these subatomic particles. Gravity wants to crush it further into a black hole, but something stops it. That something is the Pauli exclusion principle. It's the same rule that gives solidity to your chair. But here, it's not electrons refusing to share space. It's neutrons. As gravity squeezes, it packs neutrons closer and closer. But they are fermions. They cannot occupy the same quantum state. Their collective refusal creates an immense outward pressure, neutron degeneracy pressure. This quantum standoff is what prevents total collapse. It stabilizes the star. A neutron star is born. A teaspoon of its material would weigh billions of tons on Earth. Its surface is a crystalline crust of iron nuclei. Beneath that, a quantum fluid of superfluid neutrons. It spins rapidly. That's a consequence of the original star's rotation, conserved in a much smaller body. And if its magnetic axis is tilted, that beam of radiation sweeps past our telescopes with each rotation. We detect it as a pulse, a pulsar. The precision of those pulses is astounding. Some are more regular than a quartz watch. They are cosmic timekeepers. And their existence, their stability against the crushing force of gravity, is a direct consequence of quantum statistics. The Pauli exclusion principle, written for neutrons, is holding up an object with the mass of a sun. We are listening to the heartbeat of a quantum giant, a star where the rules of the very small are the only rules strong enough to withstand the force that bends spacetime itself. Every pulse is a message, a confirmation. The quantum architecture of reality scales from the nucleus to the cosmos, building clocks out of collapsing stars. That pulsar is a quantum clock, held up by neutron defiance, but the quantum world can write its signature somewhere even more extreme, the event horizon of a black hole. At that boundary where gravity becomes absolute, theory predicts a faint glow, Hawking radiation, a process that would cause black holes to slowly evaporate, fading over eons. We haven't detected this whisper from the cosmic abyss yet, but the idea itself is a bridge. It ties together three great pillars: quantum mechanics, thermodynamics, and gravity. The story starts with a related concept, the Aurora effect. Picture an observer floating in what we call a perfect vacuum. Empty, still space. To them, the vacuum is cold and dark. But if that observer begins to accelerate, to constantly speed up, their perception of reality shifts. According to quantum field theory, they would no longer feel they were in a void. They'd feel bathed in a warm glow of particles, a thermal bath. It's not because they've moved into a different region of space. It's because their own motion, their acceleration, changes their quantum frame of reference. The vacuum itself is not empty. It's a sea of fluctuating fields. An inertial observer moving at constant speed sees this as nothing. But an accelerating observer's path through this quantum sea slices it differently. They mix positive and negative frequency modes of the field. And this mixing appears to them as real particles. The vacuum becomes warm. It's a profound statement. What we call nothing depends on how we move through it. Now take this idea to the edge of a black hole. Stephen Hawking realized the immense gravitational pull at the event horizon creates a similar situation. Space-time is so warped it acts like a region of constant acceleration for a virtual observer just outside. Using quantum field theory in this curved space-time, he found black holes aren't completely black. Pairs of virtual particles, constantly flickering in and out of existence near the horizon, can be torn apart by the extreme gravity. One particle falls in. The other escapes. To a distant observer, that escaped particle appears as radiation. Thermal radiation, with a temperature inversely proportional to the black hole's mass. This is Hawking radiation. It means black holes have a temperature. They obey the laws of thermodynamics. They can slowly lose mass and energy, evaporating over unimaginable timescales. The smallest black holes would evaporate fastest in a final theoretical flash. While we await direct astronomical evidence, physicists are crafting lab experiments. They create analog black holes using sound waves in superfluid helium or light in optical fibers. In these systems, an event horizon exists not for light, but for sound or other waves. And in several experiments, they've detected the analog of Hawking radiation. Particles emerging from these artificial horizons, born from the quantum vacuum. These are macroscopic quantum effects, engineered on a tabletop. They strongly suggest Hawking's mathematics describes a real physical process. So the next time you see an image of a black hole shadow, remember the theory. That dark silhouette might one day be surrounded by a halo we cannot yet see. A halo of quantum birth from the very edge of nothing. It would be the ultimate visible proof. Proof that quantum mechanics doesn't just describe particles or forces. It describes the active, creative nature of space and time themselves. From the warmth felt by acceleration to the slow sigh of an evaporating giant, the quantum world whispers that even the most absolute voids are alive with potential. That sigh from a black hole's edge, it's a profound whisper. But these whispers, these signatures, they aren't just out there. They're not only in distant stars or in some lab. They're here, in this room, in the light on your skin, in the solid floor, in the colors on your screen. Going through these 25 phenomena, it shows you one thing. Quantum mechanics isn't some remote theory about a hidden world. It's the operating system. It's the software running on the hardware of the universe. Everything we looked at, the butterfly's wing, the flash drive's memory, the laser's line, the steady pulse of a star. Each one is a feature of that software. A visible output from an invisible code. And that changes everything. It means you don't have a separate classical world and then a bizarre quantum world. There's just one world. A quantum world that, under ordinary conditions, averages out. It averages into the familiar rhythms we call classical. The solid chair, the flowing liquid, the clear window. These aren't exceptions to the quantum rules. They're the most common consequences, so the strange becomes the standard. Superposition, entanglement, tunneling, quantization. These aren't bugs in reality. They're its foundational features, and they scale up. They engineer the materials we build with. They shape the energy we harvest. They dictate the light we see by. They set the form, the function, even the beauty of the cosmos. This synthesis, it bridges wonder with understanding. The awe you feel looking at an aurora, it isn't less when you know it's a cascade of quantum leaps. It's deeper. The gratitude for a device that stores your memories, it's richer knowing it relies on electrons doing impossible tunneling feats. You start to see through a dual lens. You see the object, and you perceive the quantum architecture that lets it exist. A rainbow isn't just a weather effect anymore. It's a lecture on wave-particle duality, painted across the sky. A white dwarf isn't just a dead star. It's a celestial monument to the Pauli exclusion principle, holding a sun's mass in defiance of gravity. That's the ultimate gift of this. It transforms the mundane into the miraculous. The world doesn't become less magical when you understand its mechanisms. It becomes more so, because you realize the magic isn't an illusion. It's woven into the fabric of existence, written in a language of probability and potential, and translated into everything you can see and touch and measure. You are living inside a quantum universe, and now you can start to read its visible signs. We've looked through 25 windows now, levitating trains, the light from dying stars. Each one a view into the quantum world, not some hidden abstraction. It's the visible architect of everything around us, and this whole journey points to one thing. Quantum mechanics isn't a remote theory. It's not just about particles in a box. It's the fundamental framework, the operating code of reality itself. Running in the open, for anyone who knows how to look. The precise beam of a laser, the impossible blue of a butterfly, the steady pulse of a neutron star. These aren't separate curiosities. They're different verses of the same quantum poem, written across scales, from the nanoscopic to the galactic. And that synthesis changes how you see things. It gives you a new kind of sight. Where you once saw a rainbow, you now see a lecture on wave-particle duality, painted across the sky. Where you feel the solidity of a chair, you now sense the collective defiance of electrons. Obeying a quantum command. The world doesn't become less magical when you understand its mechanisms. It becomes infinitely more so, because the magic isn't an illusion. It's woven into the very fabric of existence, a fabric of probability and potential, translated into the solid world, the colorful world, the luminous world we actually inhabit. So the next time you save a file to a flash drive, or watch the aurora dance, or simply look up at the night sky, remember, you're not an observer outside this quantum theater. You're a participant within it. Every sight, every touch, every measurement, it's an interaction with this deeper layer of reality.